So listening to all the talks, it's clear there's way too much geochemistry in this program. And so Matt Duchesne and I are here to represent geophysics a little bit. And I'm glad it's been recorded because I heard Paul Gellon say he was begging for geophysics. So that's an excellent sign. Anyway, I'm going to give you a quick update on 4 aspects of CO2 storage and the work we've been doing. So we'll look at tracking the CO2 plume in the subsurface. We'll look at induced seismicity, some test configurations of distributed acoustic sensing that we've done, and finally, most recently, some cross-well seismic data we've acquired. Lots of people involved in this project from the GSC, other Canadian institutions, and international players as well. So the source of the CO2 for this study comes from the Sask Power Boundary Dam Power Plant, where they've captured approximately 4.5 million tons since 2015. We get about 10% of that CO2 delivered to the Aquastore site, where the CO2 is injected and stored in a saline aquifer. So although we're looking at a power plant, as we look at carbon capture and storage, certainly this methodology is applicable to other point sources of industrial CO2 as listed here. The things we're interested in this project are monitoring the containment of the CO2, monitoring for any seismicity induced by injection. And most recently, we're trying to take a closer look at CO2 storage efficiency factors because these represent the largest unknown when we look at storage capacity estimates. And of course, the things we want to use this information for are regulations and standards development. This is a bird's eye view of the Aquastore site. On the right-hand side is the Boundary Dam plant with the CO2 capture plant as well, CO2 delivered by this red pipeline to the Aquastore site. And the green dots are the permanent geophone array. It's deployed on a 2.5 by 2.5 kilometer grid and has been used for time-lapse imaging, primarily tracking the CO2 plume in the subsurface. So the CO2 is being injected into the storage reservoir, the basal Cambrian sandstone down here to about 3,400 meters depth. Lying on top of that is a thin shale caprock. It's about 15 meters thick. And then well above that is the prairie evaporite. This is a unit that's 150 meters thick. It's very plastic, and it represents the regional seal that would impede the upward migration of CO2 were it to leak from the reservoir. CO2 injection at the site began in 2015. As of today, we have about 430,000 tons of CO2 stored at the Aquastore site. And during this period of injection, we've gone back a number of times and repeated 3D seismic surveys so that we can produce time-lapse images tracking where the CO2 is in the subsurface. These are vertical sections through the 3D seismic cubes over time. And if you focus in on the center of each of these panels, you can see that the CO2 plume is imaged and it continues to grow over time. We can also look at that in plan view as shown here. And again, you can see that the footprint of the CO2 plume is growing over time. And note that with the injection well located in the center of each of the panels, the CO2 is actually moving primarily to the east and north of the injection well. It isn't spreading symmetrically from the injection well, as was originally predicted by modeling that was done for the site prior to the start of injection. So this is a clear indication of why we need to monitor the CO2 injection over time, because models usually aren't accurate unless they're calibrated. So to note this boundary where the CO2 doesn't seem to move westward of, I put in a dashed line here. And if we move to the next slide, the outline of the CO2 plume as it grows over time is shown in the center of the slide. And that is superimposed on a seismic image from the original characterization survey. And you can see that this background image shows this lineament cutting through the slide. This is interpreted as a flexure, and it seems to be some sort of impermeable or reduced permeability boundary that impedes the westward flow of CO2 from the injection well. Just to emphasize that point, again, the dashed lines show the growth of the CO2 plume as imaged seismically over time. The orange pixelated zone represents the model prediction of CO2 flow over time. So this simulation was for the original geological model, and then a more recent one shows a model which has been updated with stochastic properties from the seismic volume. So you can see that the model used for simulation is much more accurate once we include the seismic properties. We've also been recording or monitoring for induced seismicity over the last 6 to 7 years, and that is shown on this map. And you can see the only place we see events are up near Esterhazy. These are small magnitude 2 to 3 events, which are associated with potash mining. We don't see anything in the vicinity of CO2 injection near Estevan, and there's a couple of events down here in northern Montana. So to summarize that, we haven't seen any induced seismicity over 7 years of injection. This seems to be a very stable area. And with the surface monitoring we've been doing, we think we would be able to detect events with magnitudes of roughly 0. So there may be smaller events occurring in the subsurface, negative magnitudes, but they're very small and generally inconsequential if they are happening. So one of the things we're focusing on at this stage is trying to improve our knowledge about storage efficiency factors. We have theoretical capacity estimates, but they all have these fudge factors in the formula for calculating storage capacity known as the efficiency factor. So we're trying to actually measure these. So we've gone back and we've done some cross-well seismic tomography where we put a seismic source in one well and record the vibrations from that in another well. And the idea is to get a detailed image of what's happening between these two wells. They're only about 150 meters apart. And this will give us some details about how the CO2 is being stored. So to do time lapse, you of course need a baseline. And we did such a survey back prior to the start of injection, as shown here. And the reservoir is about 150 meters thick. So you can see we're getting a very detailed image between the two wells. So when we process the new data, we should get a nice time-lapse image showing details of where the CO2 resides. This is a field shot from that survey, and we lower a seismic source down the injection well. There's pressure control equipment at the top of the wellhead, and then the geophones are lowered down in the observation well, 150 meters between the two wells, and both receivers and source are lowered down to the reservoir at 33 to 3,400 meters depth. These are the geophones that are deployed downhole. They have to be rugged. They're sitting in liquid CO2 at temperatures up to about 100 degrees C and 35 megapascals of pressure. And this is the vibratory source that goes down the injection well. So finally, one of the other areas we've been investigating is the use of fiber as a replacement for conventional geophones. Geophones are a electromechanical device. They've been around for decades. And in the last 10 years, fiber applications, where the fiber is actually the seismic sensor, are being developed and utilized. So at the Aquastore site, we actually have deployed a number of different test configurations. This is in an attempt to see if we can actually record at the surface using fiber and get good signal. And surprisingly, when we put the fiber in a shallow drill hole, maybe 3 meters of fiber loop down this shallow drill hole, we actually record good seismic energy at the surface. And this is a direct comparison of data recorded with that kind of fiber configuration that we tested against a buried geophone. So these sub-horizontal lines you see here, these are reflections from the subsurface, and you can see that the responses are pretty comparable. So as we move ahead and we install monitoring equipment at storage sites, we may be able to use more fiber, which is much easier and less expensive to deploy than traditional geophones. So I'll conclude there, and there's my contact information. And I'll just point out there, if you have access to this slide, there are links here for some movies that show some of the field deployments for this project. Thanks.